This lesson is on basic inference, specifically variability and confidence intervals. It is in Module 1, Data Science. To begin, we will discuss variability in sampling distributions. There are three main types of variability. First, variability within subjects, which is called reliability. Second, variability between subjects, or variability within samples, also known as sample variance. And third, variability between samples, or sampling variability. We will cover each of these types of variability in turn. Variability within subjects, or reliability, looks at the differences in measurements when the same subject is measured multiple times. Hopefully, the measurements are similar to one another, meaning that they have low variability. Measurements with low variability, that is, measurements that are similar to each other, are highly reliable. On the other hand, if a measurement has high variability, it has low reliability. The idea is that, under the same conditions, measurements of a variable on a subject should be fairly consistent. Variability within samples, or sample variance, comes from the idea that not all subjects are the same. Thus, sample variance is the variability that comes from measuring different subjects in a sample. If subjects are very different from one another, then there will be a large sample variance. If subjects are more similar to one another, then there will be a small sample variance. Sample variance is the variance that you see recorded in papers and articles. Many times you'll see a standard deviation, which is related to variance. We will explore this more in future lectures. Remember that a sample is a subset of a population. Therefore, there are many different samples that could be chosen from any given population. Two different samples would be made up of different people. Would these two samples provide the exact same results? For example, if I were to take a random sample of 5 students in this class and then another random sample of 5 other students in the class, and I were to average the heights of each sample of students, would I have the same average for both groups of students? Probably not. Therefore, samples, or different groups of people, may be different from one another. This is the idea behind sampling variability. Because different samples are different from each other, they may provide different statistics. Since we only take one sample, we need to account for this when making an estimate of the population. This is why we have to use what's called statistical inference. However, if samples are representative of the population, then their statistics should be relatively close together. A sampling distribution contains the values of the statistics and how often the statistics occur from all possible samples. In this graph, the x-axis, or horizontal axis, contains all possible sample means, in this case, average height. The y-axis looks at the proportion or percent of the time that the sample mean occurs. Therefore, the height of each bar represents the proportion or percent of the time the sample mean occurs when looking at all possible samples. If I took all possible groups of 5 students from this class and graphed the average height for each group, it would look like this graph. This is what is called the sampling distribution of the mean. The central limit theorem states that the sampling distribution of the mean will result in a normal-shaped distribution, or a bell curve. The center of the distribution, that is, its peak, is the true parameter. In this case, the average height of the entire class. In addition, one standard deviation of the sampling distribution is equal to one standard error of the mean, which is why we will use standard errors in the calculation of our confidence intervals and test statistics. The shape of the bell curve has a relationship with sample size. The larger the sample size, the narrower and taller the distribution will be. This is because a good representative sample that is larger contains more information about the population than a good representative sample that is smaller. Therefore, a larger sample, if it is selected properly, will provide a better estimate of the parameter. Sometimes we are not interested in the mean. In this case, the central limit theorem may not apply. However, sampling distributions of other statistics are common and also have well-defined properties. In these cases, we will use test statistics, which are statistics that are standardized or transformed so that these common, known sampling distributions can be used. This semester, we will specifically be working with T and F distributions. There are two main methods for statistical inference that we will cover this semester. In this lecture, we will discuss estimation, or confidence intervals, while the next lecture will contain information on hypothesis testing. In both cases, we will use statistics from a single sample to make conclusions or inferences about our population. To finish this lecture, we will talk about the basic idea of confidence intervals. From our previous lecture, we used statistics to estimate parameters. However, we now have this problem of sampling variability. Different samples give us different statistics. Usually, though, we only take one sample. Confidence intervals take sampling variability into account in a mathematical way. In general, a numerical summary is one number, such as a mean. Let's say this orange circle is our parameter. If I were to close my eyes and point to a place on the screen, it may be difficult for me to hit this orange circle. These attempts may be seen as our statistics from various samples. However, if I were to give myself some wiggle room, that is the blue circle around the orange circle, it would be much easier for me to close my eyes and hit a point on the blue circle. This is the basic idea behind a confidence interval. We add and subtract a little from our mean, our point estimate, to get an interval estimate that is more likely to contain the true parameter. The most common confidence interval is a 95% confidence interval. A 95% confidence interval for mu, our population mean, is created so that 95% of like intervals will capture mu and 5% will not. The sampling distribution of x bar, our sample mean, shows mu at the center. In this example, there are 5 sample means. The dotted line going up from each sample mean shows where it falls on the line of all possible sample means. The solid blue line descending for mu shows its extension down near each sample mean. Though some of the sample means are close to mu, none of them are the same as mu. However, by creating an interval, 4 of the 5 sample means cover the true parameter. If a statistic falls in the 95% range around the true parameter, the interval will hit or cover the true parameter. Otherwise, it won't, as in the case of x bar 3. In order to create a confidence interval, you take the point estimate, that is, the statistic from your sample, and subtract and add the margin of error. The lower confidence limit is the point estimate minus the margin of error, while the upper confidence limit is the point estimate plus the margin of error. This is the basic format for every confidence interval you will ever construct. How you calculate the margin of error depends on the data you have. The margin of error is simply a mathematical way of calculating sampling variability.